EPRI has invested more than $2 million since 2012 in its state-of-the-art microscopy and metallurgical labs. This capability allows EPRI engineers to study microstructural features in ex-service materials, failures, or laboratory-generated samples at the macro, micro, or nano scale. In principle, EPRI examines every sample at the macro scale before deciding to progress the metallurgical examination to a micro or nano level. Received samples are examined using a 3D handheld laser scanner to facilitate reconstruction using CAD software. The equipment used for this purpose has a sub-millimeter resolution on the order of 100 microns or less. Before machining, the part may be assessed in 3D using a state-of-the-art LED microscope with a resolution on the micron level. Failure surfaces, pitting, or other topographical features are often imaged using this equipment. Subsections are removed and rough machined to size in EPRI's fully equipped machine shop before being metallurgically prepared. EPRI technologists, using their decades of cumulative experience, implement and optimize polishing procedures to facilitate the preparation of a diverse set of material types. Specialist preparation equipment includes capabilities to cold or hot mount, prepare very large macro samples, or finish surfaces in a vibratory polisher. Polished samples are first imaged in this as-polished or etched condition using optical microscopes. EPRI has invested in microscopes with the latest advancements in imaging to obtain very high-resolution optical images in 2D or 3D. EPRI acquired the first dual detector micro XRF system of its type in the US when installed in 2020. This instrument can map the distribution of alloying elements over very large sample areas. For example, welds in high-energy piping systems where the through thickness and/or width is measured in the tens of millimeters or inches. This system has spatial resolution of approximately 20 microns. Since the purchase of its first hardness mapping system in 2012, EPRI has procured 3 additional systems, developed procedures, and generated more than 2 million hardness indents. The largest single hardness maps measure in the tens of thousands of indents, and this capability is routinely used to characterize heterogeneity in welds or as manufactured components. The field emission gun scanning electron microscope installed in the EPRI laboratories has a very large sample chamber and is equipped with multiple imaging and analytical detectors. Image collection is enhanced by specialist software to collect images over very large areas that can be subsequently analyzed using image analysis software like ImageJ or MyPar. Energy dispersive X-ray spectroscopy, also known as EDS, is used to assess local elemental distribution and provides a means to execute semi-quantitative compositional analysis. Electron backscatter diffraction, also referred to as EBSD, is an analytical technique used to investigate local crystallography and material texture. This capability has been extensively used to clarify variable microstructures, phases, or provide a qualitative basis for assessing local variations in strain accumulation. Frequently, comprehensive investigations may require the use of facilities that are not currently available to EPRI engineers. In these scenarios, EPRI engineers execute or contract microscopy through long-standing university relationships. This process leverages reputable university researchers, unique capabilities, and provides findings critical to the fundamental understanding of underlying damage or degradation of mechanisms. As new technologies emerge, EPRI will remain at the forefront of investing and utilizing these capabilities to revisit prior research outcomes, analyze industry failures, and inform future research projects. Advanced microscopy will remain a cornerstone in the EPRI laboratory offering in the decades to come.